Hello everyone, welcome back. So we're doing another problem with the mass of inertia, as well as calculating that radius of gyration. So what we have here is another pendulum, and it's got a plate right here. Whoops, sorry, went crazy a bit there for a second. And a thin rod right here. And it says it wants us to find the radius of gyration about an axis that is perpendicular to the screen and passing through this point G, which is the centroid. So how are we going to do this? Well, we're going to have to figure out the mass of inertia for our two bodies, and then also determine the radius of gyration using the mass of inertia and our mass values. So let's jump right into it. First off, we're going to separate this into two little parts right here, a plate and a slender rod. And then we have to go ahead and calculate the centroid. So what we do here is we say, okay, where is the center of gravity of each of these points by itself? We multiply that by their mass. So this is more or less just a weighted average of their centroids. And then we solve. And so what we get then is going to be 1.781 meters. Now, where is that from? Where is that measured from? Well, let's do a little bit of detective work here. First off, the rod here has a mass of 3 kilograms. And it is too long. And so what we're measuring from is right here. This is our origin for terms of measurement. So it's 1.781 meters down from the origin. So that makes sense. Now, knowing that, we can use the data on plates and cylinder rods that's given in the inside cover of your textbook. And so for that plate, it's simply 1/12 the mass times its dimensions. So its width and its length, each squared and then added together. For that slender rod, it's 1/12 times the mass times its length squared. And then what we have to do is we have to add in the parallel axis theorem. So we take their masses and we multiply by their distance from the centroid, or the center of gravity in this case, I guess. And one thing to note here is that it's squared, so it doesn't actually matter that it's positive or negative. It's all going to come out nicely in the end. Then what we know is that the moment of inertia for a composite body is the sum, the algebraic sum, of the moment of inertia of the individual things here. I'm saying moment of inertia, the mass moment of inertia. It's just a little bit quicker to say. And what we get is it's going to be 4.45 kilogram meters squared. So that's our mass moment of inertia. We know the masses, we know the mass moment of inertia, which means that we can easily calculate the radius of gyration, which is going to be 0.746 meters. Now, if you're wondering, what about how do we know that this is the radius of gyration around that axis? It's because it's the moment of inertia around that axis, and that's what's controlling everything. So it gets its connection through the mass moment of inertia. But that's it for this problem. You use the inside cover of your textbook, you use the parallel axis theorem, and you prosper. It's one of those things that's kind of just a plug and chug. But if you're really struggling to understand what the mass moment of inertia is, remember this, that it's telling you how difficult something would be to accelerate, to have an angular acceleration for that object. So the higher your mass moment of inertia, the more difficult you are to start twisting. Like you apply torque, it's going to take a lot more torque to cause an angular acceleration, at least a appreciable angular acceleration. So that's it for this time. Thank you for listening, and I'll see you all later. Bye-bye.